somebody else has something prepared. So it's a pleasure for me to present you to Amram Eshel, that everybody knows, of course, and his title will be Fractal Dimensions of Root X-ray Computed Tomography Images, a measure of their volume filling capacity.
Thank you. It's a work with the help of Saoirse Tracy from Dublin at the moment. We've all looked at many pictures of roots, and they look. The question when it comes to it, how do we describe it? How do we characterize how is this root system different from the other? And we've heard a lot about quantitative estimates, measuring length, measuring surface area, and so forth. You can divide the total length by the certain volume of the soil and get the rootlet density, but you don't know where are they distributed. And some people are trying to then go deeper into various components of the root system. And you're very familiar with all these false presentation of 2D spread, which are non-realistic, totally missing the 3D dimension of the root system, but they are nice to look at. People have compared models on one side with those kind of drawings, on the other try to recreate this complexity of the root system. We've all heard of the SimRoot model and its uses of various types of analysis of what the real root system would do. And we've heard about a large number of parameters you can use in order to characterize the architecture. The problem, as I see it, one of the problems with it that Boris also mentioned too, they are not correlated to one another at all. It's easier to look here. You measure two parameters, very common ones. There is a variability in each of them, but there's no correlation between one another. So you end up with a large matrix of a lot of data, which are confusing to say the least. Here is another example from a recent publication that you get sometimes positive, sometimes negative, sometimes no correlation at all between all these parameters of architecture. Then what do you do? And here is another one. What happens when you try to hybrid two genotypes? Some parameters show an altered distribution, some parameters don't. And what is the conclusion? The question is then how to grasp all this complexity and how do you describe it? And here come to the help came Professor Benoit Mandelbrot in 1983, published his book about fractal geometry. And he said that the regular or the Euclidean geometry, which dealt with objects of either one dimension, straight line, 2 dimensions, planes, or 3 dimensions, volume of some sort, they're not applicable to natural objects. Natural objects, he said, are fractal. They have dimensions between 1 and 2, and between 2 and 3, because they don't feel all either the area or the volume we assign to them. They are porous, and then they sort of spread all over the volume you let them to, but they never fill it. So you get a certain fractal dimension, which is either 1 point something or 2 point something, that describes how well the object fills the total volume. And his book has a large section about the mathematical fractals, about their unique property, the self-similarity, the independence of scale, and so forth. But he also talks about the natural fractals, the fact that objects, and all natural objects, not man-made, are fractal, are filling a certain volume in a certain way. And this can be for you either clouds or mountains or salt grains or whatever. That's what they look like. And there are many other examples of what natural fractals are. These are, for example, colonies of bacteria on the agar plate, and rivers and so forth. So, and he has many compelling examples to prove that natural objects are fractals. And there is a link. There are many computer programs now that produce fractals that look like some branched natural systems. And after this was published, people have grabbed it to describe various natural or biological structures that fill a certain volume and use a finite volume. Here is an example from blood vessels in the lung. Here are some shapes of various algae, and so on and so forth. People used it for various objects. And how do we determine this fractal dimension? What's the trick? How do we know what the fractal dimension is? So if this is our object, we divide it into squares, and and we count the number of squares intersected by our object, and we divide it by smaller squares and smaller yet, and so on. And we get on 2 log scales, we get the number of squares intercepted and the size of or the number of squares we have on the side. So of course, the smaller the squares, we have a larger number intercepted. And if we get a straight line, this obeys the mathematical rule of fractal, and the slope of this straight line is the fractal dimension of this object you're using. And a few years after, root scientists also wanted to try it, and this group realized they cannot analyze a 3D system, so they spread the parts of their root system, and here is how they counted the number of squares of different sizes, and the results are that the root systems they've analyzed are very close to fractal. You see in the high end here there is some deviation from the straight line, but it's mostly a straight line, pretty good one. And here are 2 of corn, millet, and wheat, and they got the 2 fractal dimensions of these root systems. Another example a few years later, where they've grown maize in 5 centimeter wide boxes, sort of gotten similar to a 2-dimensional root system of the maize, have laid it, and they've shown that you can determine the fractal dimensions, and it's highly correlated with the size of the root system. The older the plants, the larger the root system, and the higher is its fractal dimension. So it stands to reason, but it doesn't help much yet. We could just measure the size of the root system and know what it is. Doesn't bother with the fractals. I took the advantage of the fact that these dwarf tomatoes have dwarf root systems and very stiff ones. You can put them in water and they don't droop. They keep their own positions of all the roots. I've immersed them in gelatin, immersed in gelatin, and then I could cut them into slices and digitize that and do the trick of the analysis and determine the fractal dimensions of various parts of this root system. So overall, the root system of this dwarf tomato had a 1.5 fractal dimension with the very high correlation. And once you have it digitized, you can play with it. You can sort of virtually cut it into slices. Here are vertical slices, and move them along the x-axis and see that this root system is pretty symmetrical, has the higher fractal dimension in the middle and fewer roots and lower fractal dimension at the sides, and you can get some idea of what does it look like. About the same time, publication from a group of Douglas Goldblood done on fruit trees in Africa also have found that the more volume filling, the more intricate, the more complex root systems had higher fractal dimensions than the other two, which had more sparse root systems. The problem with it is the collection of the data. I've also tried several greenhouse-grown vegetables, and it was very tedious to collect the data at a high resolution, which is what you need. Even if the root system is large altogether, the volume is large, you need the data at high resolution in order to do the calculation and determine the fractal dimension. This was the limiting factor in all this work. Whoops, sorry. And here came Tracy to my help from a study she made in the University of Nottingham, the group of Professor Sasha Mooney, where they've grown tomatoes for 10 days in 2 soil types, clay loam and loamy clay, and sorry, oh, see it in a minute, I forgot their names, and they were either compacted or non-compacted. And as you can see, roots grew pretty well. Oops, sorry. In the clay loam, there was a little difference between the 2 treatments in overall root length. There was some, but in the loamy sand, there was a great difference. The non-compacted soil allowed much larger root growth than the compacted one. There was not much effect on the root diameter in this case. And she was kind enough to send me 4 images, 4 of these scans, 1 of each treatment, which I've digitized. And in order to calculate the fractal dimension, I needed an overall box of a multiple of 2, or power of 2 size. So I had to add a little empty space here and cut some of the empty space at that part, try to include the whole of the root system as I could, and I got this 1K cube for which I did the analysis. And here is an example of the compacted clay loam, which had a 2.15 fractal dimension, 3-dimensional fractal dimension. And again, you see a little deviation from the straight line, but it still obeys the fractal rule. And this is the main result of the slide. The only slide I would like you to look at in all this lecture. We could compare each of the soils and the 2 treatments. And in the clay loam, we get some different in size. Yeah? In the uncompacted, they are somewhat larger than in the compacted. They both have fractal dimensions. But here, contrary to what I expected, in the compacted soil, we had a higher fractal dimension. The roots were more sort of convoluted and filling the volume better than the somewhat larger root system in the uncompacted soil. And in the loamy sand, where the differences in sizes were much larger, similar to what you've seen in the averages, again, the fractal dimension in the compacted soil was much larger than, or was significantly larger than in the uncompacted soil. So I think that this indicates that the fractal dimension describes here a certain characteristic we're looking for, how well the roots fill the volume independently of their overall root size. We can play again here with the same way, cut it into slices vertically, as here the root system was not that symmetrically distributed. And whoops, sorry. This is the regression. We get a very large portion of it where we have the higher, most of the roots, very high R squared, so they are fractal in this area. This is how the fractal dimension varies along the x-axis. And we look at, among all these x-axis, the amount of roots versus the fractal dimension. You see at the lower end, there is, of course, a high variation with a very low variation with root size at the higher end. And, whoops, no. In another article, we have the soil scientists have analyzed soil porosity, which, as hope you'll agree, looks very similar to the distribution of roots in the soil. They got exactly the same kind of distribution. So whenever you are at the higher part of the root system, you get some variation, but not very much in the fractal dimension. And Jonathan Zinn's group have done many such studies also of real root systems. Here is one from beans. And the 3D fractal dimensions here again vary some with the growth of the roots. And they also advocated combining it with another parameter which didn't, in my idea, didn't give much additional information. So my main message for you is consider the fractal dimension as the parameter to characterize this efficiency of the root system in using or utilizing and spreading within the root volume, which is in many cases, especially in agricultural cases, an indication of the efficiency of the root system that we want to have. And it's a single parameter you can use, and you can correlate with other phenological characteristics of the things you're interested in. Thank you very much.
Thank you very much, Amram. Questions?